We now have a new definition of gravitational potential energy between two masses. We'd like to apply this now to the problem of escape velocity. Escape velocity is the absolute minimum velocity an object, such as a spaceship, needs to attain to escape, notice I have it in quotes there, the Earth's gravitational pull. Actually, since the force of gravity has an infinite range, this is never really possible, but the force really gets tiny at great distances pretty quickly. We're going to use conservation of energy, and our system is going to be the Earth spaceship system. If we're looking for the minimum velocity, what magnitude of the potential energy and kinetic energy of the spaceship will we want when it is at an infinite distance from the Earth? Almost by definition, since we're looking for the minimum required velocity to escape the Earth, we want it to get to infinity, the spaceship, with zero kinetic energy. We've already defined potential energy at infinity to be zero. A practical reason for this is it's very expensive to put spaceships into orbit. You need a lot of fuel. So if you shoot the rocket off way too fast, you'll get into orbit, but you're going to spend too much money on fuel, so you want enough to get there. Of course, with safety margins, this is where the engineering comes in. But still, you don't want to spend more fuel than you need. So let's look at our conservation of energy equation. Here's our initial kinetic energy and gravitational potential energy. Here's our final. So we know we're going to take off with a certain escape velocity, 1/2 mv squared, and you can see the subscript here, escape. We have a certain potential energy on the surface of the Earth. Remember, in the past we would just think potential energy is zero, but now we know we have an actual number for it, because this time we're using potential energy at infinity as zero. Recall the graph, and please back up the slides if you'd like and look at the graph again. So your initial potential energy is a negative here, negative g/m/r, and at infinity we want this kinetic energy and potential energy to be zero. We put this term on the right side, multiply through by 2, do a little more algebra, and we find out that the escape velocity is the square root of 2 times universal gravitational constant times the mass of, let's say, the Earth, if that's what we're leaving, divided by the radius of the Earth. Note that the escape velocity, right over here, is independent of the mass of the escaping object. It only depends on the mass and radius of the object being escaped from. So let's use this fact and think about why, despite the fact that hydrogen and helium are the most abundant elements in the universe, there are only trace amounts of each element in our atmosphere. When the Earth was first formed, hydrogen and helium had significant presence in the Earth's atmosphere. However, they are also the lightest elements. So for a given atmospheric temperature, they would move faster than the heavier elements. Over time, their average speeds exceeded the escape velocity of Earth, thus they left the planet.